Hello, students. This is a really quick review of some pre-calc pieces that are going to allow us to introduce the derivatives of sine and cosine. This is section 2.5, part of 2.5 from your textbook. So we're going to do a quick review of some pre-calculus items here. If you think of the unit circle is going to help us generate the graph of sine x. So if I want to find the sine at 0, remember in your four quadrants, and we're only looking at the four quadrants, you could get more accurate if you wanted to, but every ordered pair is cosine and sine of that radian. So if I want to find the sine at 0, well, sine of 0 or sine of 2 pi is 0. So I'm going to put my first point at 0, and then I'm going to go to 2 pi. Well, 2 pi is 90 degrees. The sine at 90 is 1. And then I'm going to go to pi, which is 180 degrees. The sine of pi is 0. And then we're going to go to 3 pi over 2, and the sine of 3 pi over 2 is negative 1. And then if I go back to 2 pi, the sine of 2 pi is 0. And there's the first, sorry about that. This one should be over here. 3 pi over 2. Okay, so here's the first period of sine. Starts at the midline, goes up to the max, down and back. Now, this is periodic, so it repeats. I'm going to finish this really quick. Okay, so you can see I finished sine. Remember, it's periodic, so it just follows the same pattern. I also did cosine. Cosine of 0 is 1, so that tells me my starting point is up here at the maximum. Then we go to the midline, minimum, midline, maximum, and so on. Well, why is this important? Well, for many reasons, but one of them is we're going to use this, and here's a better graph of sine. Notice it doesn't have this in radians, but at 2 pi, which is just past 6, this would be 2 pi right at the end. Halfway through would be pi. Half of that would be pi over 2. So we're going to use these same ideas, but now we're going to look at the slopes. I'm going to just kind of generate a quick little table based off the slopes of the tangent lines at these points. And I'm going to do this kind of hopefully quickly here, just so we can kind of get an idea. One of the easiest things to do is identify horizontal tangents. So if I drew a little tangent here, I know the slope is 0. Well, where is that? That was halfway to pi. So that's pi over 2. So at pi over 2, my slope is 0. And then if I go to pi, right here, what is the slope at pi? Well, you're going to have to trust me a little bit on this, but if I was to draw a line here and actually calculate it out, that slope is going to be 1. But notice the direction that it's headed in. So now my slope here is the negative 1 at pi. And then notice right here, this would be 3 pi over 2. That has a horizontal tangent, so its slope is 0. And then if I go to 2 pi, I could bring the ruler over and measure it again, but its tangent line would be increasing at the same rate as it would be pi. The only difference is my rate is increasing here, so I have this positive slope of 1, and that would be the same thing right here at 0. Slope would be 1. Now, you could keep doing this, but these are good enough points here. What did I do? I generated the slopes of the tangent line at x. Wait a minute, doesn't that have a special name in calculus? That's the derivative. So what I'm going to do now is take these points, and I'm going to plot them on a new graph, and this will be my graph for the derivative. So if you're ever creating a graph, make sure you label it. If I call the top function y, then this bottom function is going to be y prime. And let's just plot the points. When x is 0, I'm going to set my x or my y scale here. Let's just expand it out. Let's say that's 1 and this is negative. So when x is 0, I've got a point right here at 0. Oh, excuse me. No, sorry. When x is 1, the slope of the tangent line was 1, so I'm going to plot that as an output. So 1, 0, or 0, 1. Then I'm going to go over to 2 pi. And 2 pi had a slope of 0, so I'm going to plot its output. And then go to pi. Pi was negative 1. That was the slope at negative 1. I should have lined these up so you could see here's -1, its slope, and that's the point down here. And then the next one, go over to 3 pi over 2. That had a slope of 0. And at 2 pi, the slope was 1. So doesn't this form a familiar pattern? Look at this graph. It's periodic, and it starts up here at 1, and then it goes to 2 pi, pi over 2 as we go through. Wait a minute. Isn't this graph the same thing as cosine? Which is true. The derivative of sine is cosine. All right, we're going to write that down in a second, but let's take a look at this next one. What if I do the exact same thing at cosine, and I'm going to sketch a graph of the slopes of the tangent line. So I want to go here, and at 0, I've got a slope of 0. At pi over 2, pi over 2, if I drew the tangent line in here, you can see the slope. I'm going to just trust me on that, but it is -1. If I go over 2 pi, that's halfway through the period. That has a horizontal tangent, slope is 0. And then here at 3 pi over 2, its slope is 1. So pi had a slope of 0, 3 pi over 2 had a slope of 1, and then this would be 2 pi right here, and its slope is another horizontal tangent. So using those same patterns and that same idea, let's graph these, and maybe you're already kind of think of where we're heading. Take a guess right now. What do you think the derivative of cosine is? Well, let's look at it. If the derivative is just the slopes of the secant line or tangent lines at all those points, let's graph it. Now I'm going to start at 0, 0. But then I'm going to go over to pi over 2 and down 1, and let's set my scale here. So I'll go from -1 to 1. So my first point is at 0, 0. Next point, go over pi over 2, down 1. And then at pi, we're back to 0. At 3 pi over 2, we're up to 1. And then 2 pi, we're back to 0. Now, this looks really familiar. The function that starts at the origin, 0, 0, is sine. But the graph of sine usually went up to a maximum. In this case, my graph now went down to a minimum, which can be a very helpful hint. Sine starts, so I know my answer is sine. The derivative of cosine is sine, except for it reflects down and it goes to the minimum, which makes it negative sine. All right. So grab your notebook. Those of you that created the list of derivatives in your notebook, we just have 2 new fun facts. If f of x is sine, then its derivative, the derivative of sine, is cosine. If g of x is cosine, the derivative of g of x is negative sine. Think of those as new facts. Now we can use them. Let's see how to use them. Okay? We haven't really done this, but actually, you can keep taking more and more derivatives if you'd like. Let's try this. The derivative of sine. So find y prime. Well, we know that. That's a fact. The derivative of sine is cosine. Oh, wait a minute. Can't I take the derivative of a derivative? We're just going to put 2 prime marks there. So this is the second derivative, but the derivative of cosine is negative sine. And now, what if I take the derivative of that? So this would be the third derivative, or y to the 3 prime. Well, notice this negative is like a constant. It's like a -1, so you could just sneak a 1 there. And that's going to come down. So I'm just thinking the derivative of -1 times sine. While -1 is going to stay, derivative of sine is cosine. So notice its derivative just stays negative. And then finally, the last one. So you could probably use Roman numerals. I'm just going to put 4 tick marks just so we know it's the fourth derivative. But let's take the derivative of negative cosine. Well, the derivative of cosine is negative sine, so a negative and negative is going to turn into a positive. And there we go. There's the fourth derivative. And you could just keep on going. And actually, look at, didn't we just repeat where we were before? So if this was the original function, 4 derivatives gets me right back to where I started. All right. Well, what else can we do? We can use those fun rules we just learned the other day. Product rule and quotient rule. Well, look at this. I've got y equals 2x to the third times sine of x. So I'm going to set up and I'm going to call the first function u, the second function v. And I like to show some work here. I call this side work. So let's call u 2x to the third, and let's call v sine x. Well, to do the product rule, we need the actual derivatives of each piece. And this is just our power rule. The 3 is going to come down and multiply by the 2, and we're going to take one away from the exponent. And then for the sine function, we know the derivative of sine is cosine. So think of that as my work. But now I'm going to do the product rule. And how do I know it's product rule? Because they're multiplying two functions together. And what was the product rule? It was the derivative of the first times the second plus the first times the derivative of the second. So let's just plug in what we know now. U prime is 6x squared, and we're going to multiply that by v. You can see u prime times v, which is sine of x, plus u times v prime. So what was u? U was 2x to the third times cosine of x. And that's as far as I'd go. You could simplify and you could pull out a common factor, but I wouldn't. This is good enough. All right, next one, last one here, I believe. We're going to do the quotient rule. We've got a fraction, sine of x over cosine of x. So just really quick, what is the quotient rule? Well, it's very similar to the product rule. The only difference is we take the derivative of the first times the second, but now we're going to subtract the first times the derivative of the second all over the second one squared. So again, we need that same little side work we did over here. I got to figure out what is u. This should look like a u. That's even worse. That's a u. So the u is the top function. It's your numerator. And we know the derivative of it. Derivative of sine is cosine. And then the bottom function, the denominator, that's v. And I need the derivative of v, which is negative sine. Think of that as my side work. And once you know that, plug it into the quotient rule. So we're looking for the derivative of y, and we're going to take, let's separate this by a subtraction. We're going to take the derivative of u, which is cosine of x, times v, which is cosine of x. Interesting. And then we've got u times v, so sine of x times, now I should be careful here, this v prime is a negative, so I'm going to put parentheses around that. And then it's all over v squared, so cosine squared. Well, there's some really interesting things here. If you stop here, you're technically done with the quotient rule, but let's look at kind of some interesting pieces that go on here. Cosine squared and cosine squared, or excuse me, cosine times cosine is cosine squared. And then what happens when I have a negative sine times a negative sine? That's going to turn into a positive sine squared of x. And then we're going to just leave cosine, I'm going to actually do it like this, cosine of x squared. So how can that simplify? Well, if you look at the top part, it's our trig identity. We haven't talked a lot about that yet, but it's one of the more familiar ones from pre-calc. So I'm just going to simplify that. Cosine squared plus sine squared is 1. And then I've got cosine on the bottom. So if I notice how I didn't write the squared yet, partially because I want to put brackets, but I could also put a squared up here because one square doesn't change it. So technically, I could pull this out. And what do we have? We've got 1 over cosine. Well, wait a minute, isn't that also a trig piece? 1 over cosine is the same as secant, and then that squared is going to come into play. My answer is secant squared. The derivative of sine over cosine is secant squared. Wait a minute, isn't sine over cosine just tangent? Oh boy, we just found the derivative of tangent. So you could add that to your fun fact. If y is equal to tangent, then the derivative of tangent is secant squared. That's not in this unit, but it's coming up. So kind of cool how we generated derivative of sine and cosine from a graph, and then we use their derivatives to figure out the derivative of tangent. All right, this is a little fun one. Last one. What if I go backwards? There's a pretty interesting piece here, and this is the derivative of h of x is negative 2 cosine of x. Well, whose derivative gives me negative 2 cosine of x? Well, the 2 is just a constant, and this negative could actually be brought to the cosine piece. So I could really think of it like this. 2 is just a multiplier. So h could just be 2 times whose derivative gives me negative cosine? Well, that's sine. Oops, I forgot my x. So that's just a little fun thing you can do is work backwards. We're going to be doing that later on, and actually you'll find out later that there's a constant here that when I take the derivative of this answer, the derivative of the constant goes away. So it could be anything there. The plus c could be any number, any constant. All right, that's all I got. Enjoy the video. We'll talk more about this.